So now in the next task, let's try to determine the stresses of each element. So for this, we can use the equation which we derived in the previous session. It's 5 point, let's say 2.36 equation, if I can remember. Just check and whether this is right. Yeah, equation 5.2.36. So we can express the stresses applied to each element using again the constitutive matrix, the B matrix, and the displacement matrix. So for element 1 and element 2, we can apply this equation again. In the supporting material, you would see it how I have applied this equation and obtained the stresses and the corresponding stresses for element number 1 and element number 2, which I will not write down again because D is the constitutive matrix. B relates to again the B matrix, which is defined by gamma and beta and gamma terms, and the displacement matrix, which we already discussed. If we take the element number 1, of course, we are talking about displacements of node number 1, node number 3, and node number 2. So I, J, and M. Okay, I, J, and M, 2I, and similarly, check I, J, and M nodes. If we talk about node number 1, yeah, 1, 3, and 2, and if we talk about node number element number 2, we are interested in writing down D1X displacement matrix, D3X, J refers to node number 4, 4X, D refers to node number 3. So this is for element number 1 and element number 2. This is the only difference, and the corresponding stiffness made, you can use the corresponding stiffness B matrices depending on the different nodal coordinate systems, nodal coordinate values. So what we obtained for element number 1, if you substitute the equations correctly, supporting material which provide so the reference 5.4.30 equation, by solving 5.30 in supporting material, we obtain the stress matrix which has 3 terms: stresses in x direction, stresses in the y direction, and the shear stress for element number 1 would be something like this. And for element number 2, again using the same equation, the set of equations, the three components would be you would obtain it as 995 pounds per square inch, and the stresses in the opposite direction, of course, pounds per square inch. So now you have obtained the stresses applied in X and Y, and of course in the XY plane, the two stresses, the normal stresses as well as shear stresses of the two elements. Now, based on these stress values which you obtained, now you can determine, of course, the principal stresses as well as the principal angles for the two elements. Yeah, for you can simply apply it for element number 1 and element number 2 using maybe the equations, if you can recollect. The principal stresses can be obtained using for element number 1, we determine, let's say, for element number 1 and element number 2. For element number 2, so for element number 1, it will be similar. For element number 2, we can write down the principal stress in terms of, let's say, the X and Y stresses, normal stresses as well as the shear stresses. Yeah, so the two normal stresses would be with the plus sign, and with the minus sign you would obtain sigma 1 to be 995 pounds per square inch. So second normal stress would be minus 1.1 pounds per square inch. Similarly, you can obtain the principal angles for the single stress, and of course the two angles between the two principal stresses would be 90 degrees, that is we are perpendicular to each other. So what can we say from the results which we obtained, that we already know that we can calculate, or what we are required is, now we need to quantify whether this is whether the results which we obtained is okay, or whether the system which we model would fail under certain conditions. So we will be using the stress values which we calculated in the X direction, Y direction, the normal stress values, of course, in the X direction and Y direction, as well as the shear stresses in the XY plane, to get an idea about the material behavior, or whether the system would fail or not. So this is exactly what you do also in the simulations when you obtain, when you finally calculate the results. You calculate the different stresses, particularly for different elements, and you would see whether the material is able to withstand this, withstand the boundary conditions. So probably you have already done this already in your, let's say, simulations when you ran in your lab classes. So especially when we talk about, let's say, analyze about the results, we use the von Mises theory. Yeah, so we also call it the maximum distortion energy theory. also known as von Mises. It should be von Mises, not von Mises. I mean, this is a French term. Von Mises, or von Mises Incan theory, which is applicable. Von Mises theory applied for ductile materials. These are applied for ductile materials. Which is subject to static loading conditions, of course, whether the material will be able to withstand this, the stresses applied on the material. So what we do is we calculate the von Mises theory, or we calculate, if you can remember, you use the von Mises theory, von Mises stress equivalent stress, which is nothing but so we do it for each element in this case, of course, which is nothing but which can be obtained using the principal stresses. Or if we talk in terms of, let's say, X, Y, and Z components, stress components, we can write it down using the X and X, Y, and Z stress components. Of course, since we are dealing with constant strain triangular elements, the normal stresses applied in that direction is negligible. That is our conditions. So we can simply exclude the irrelevant terms. The relationship, we can remember, x also yz squared is something like this. So the von Mises theory, defines the von Mises stress criteria using the stress components in the x, y, and z direction, as well as the corresponding shear stresses applied in xy, yz, and zx planes. And the yielding criteria, the criteria for yielding, is given in terms of the yield strength of the material. So for the system, or for the model to withstand, the equivalent von Mises stress should be larger than or equal to the yield strength of the material. If this let's say, if this condition is violated, we that is if the equivalent von Mises theory is larger than the yield criteria of the yield strength of the material, then we say at a particular location the material fails, at a particular element the material fails. Then we have to use a suitable material with a higher yield strength for a particular instance or a particular location of the material of the total model. So as you can see, the von Mises stress is nothing but a scalar quantity which measures the intensity of the entire stress. It gives an indication of the entire stress state of the stresses using either three principal stresses, or let's say three normal stresses in the x, y, and z directions, combined with the shear stresses in x, y, and z planes. So this is a very good criteria, very effective criteria, which we use commonly in mechanical engineering to see whether the material has failed, or whether a model will fail subjected to certain boundary conditions. So you will be using this, if you have not already done so, in the lab sessions. to check whether certain parts of a geometry or a model will fail or not. And based on your conclusion, you can refine the model. You can introduce new materials to certain sections and see whether the model can be improved or withstand, so that it will be able to withstand certain boundary conditions. So commonly other conditions such as maximum principal stress, or let's say um, um, uh, by considering only the maximum principal stress, also used commonly sometimes to obtain a judgment whether material will fail or not, which is not that effective. So and which is not very accurate in predicting a material failure. So most of the computer or finite element simulation programs have incorporated this yielding criteria or von Mises theory to check whether the condition of the stress state or stress intensity, stress distribution within a material, and it conveniently provides the user using a graphical representation by plotting the one equivalent von Mises stress throughout the material, so that you as a finite element analysis would be able to identify whether there are stress concentrations and whether these stress concentrations can be tolerated for a given material, or whether it exceeds the yield strength of the material, and whether further modifications are required to improve the stress states, improve the condition of the model. So based on such judgments, based on such plots, graphical plots, you can conclude about the behavior of a material based on certain boundary conditions. So a point you need to remember is the equivalent von Mises stress should be lower than the yield strength of the material. Otherwise, it will fail. So if, of course, this cannot be directly used for any type of material, it can be only used for ductile material. And if there are brittle materials, of course, such as, let's say, cast iron, let's say, or let's say glass or other type of ceramics, having different, let's say, tension and compression properties, it is recommended to use for brittle materials. One can use the Coulomb-Moore theory. The Coulomb-Moore criteria or Coulomb-Moore theory to determine or to predict the failure behavior of such material made out of, let's say, brittle components. Yeah. So I think now it's clear that that you have understood that it is important to have a good idea about, let's say, what type of element you will be using and what is the theory based on the type of material which you have to use to obtain a judgment or to predict the failure of a certain component when you are doing certain analysis. So we already have used constant strain triangular elements for modeling the systems. As you saw from the analytical results obtained from the beam theories, there were certain deviations and we attributed it to the coarseness of the mesh. But apart from this coarseness of the mesh, even if you use highly, let's say, very large number of elements and use a computer program to run a simulation, you will still see that there are certain deviations taking place in certain instances. For example, there are certain limitations when we can use constant strain element, triangular elements, especially in connection with bending problems. So because if you use constant strain triangular elements for modeling bending problems, the elements or the constant strain triangular elements will generate a model which is kind of like stiffer than the actual scenario, because the term constant strain, which is not really applicable for bending problem, and um, in particularly for bending problems, the strain will change kind of linearly within the element. So to address such problems, in order to mimic the real scenario, where especially in applications where the stresses is not constant within the element, but it changes kind of linearly within an element, we need to we need to introduce, or we need to use another type of element. So in such instances, we use linear strain triangular elements, where the strain now varies linearly within an element. As you can obviously think that this linear variation also comes with an additional computational cost, meaning we will have to introduce more number of degrees of freedom. We need to use more sophisticated, let's say, more number of degrees of freedom means we need to use more sophisticated shape functions, also to capture this linear variation of the strain. So the problems will become a bit complicated, and it will become a bit hard to do simple calculations using a pen and paper, and you need to resort to computer programs, numerical simulations, to solve such complicated problems. Yeah, so in the next session we will quickly, without going into details, try to understand the concept of the linear strain triangular elements. We will not, of course, we can derive the stiffness matrix, element stiffness matrix for a linear strain triangular element. We call it an LST element. It is the same procedure that we have to go through, which we use to derive the constant strain triangular element matrix. So we will not be really going into details, but let's directly try to get an idea as to what is really happening when we use, or when we try to use a linear strain triangular element. And let's directly go into a problem and try to solve a problem to get a of using a LST model, LST element within an FEM simulation. And also I will be uploading, let's say, some of the supporting material which will be quite useful or handy when you are running simulations. Some of the practical consideration which you need to know as a finite element simulation, let's say, engineer who will be running finite element simulations. It is not simply clicking buttons, but we have to make sure that you are in control of the simulation. That is, you define a certain mesh, you apply certain boundary conditions, and you analyze the results with a clear idea, or without directly accepting the results provided by the computer. So the practical considerations which I will be uploading, the supporting material, which be quite helpful for you to make a prejudgment whether you are running a correct simulation, or whether you need to improvise it, or whether you need to change the model which is given by the computer. Yeah, so obviously these algorithms are highly sophisticated and be optimized, but computers are just let's say, it follows commands. There can be certain errors. So if you are really confident, or if you really have an idea as to how the models should behave, then you can get the optimum output from using the computer simulations. So read these through materials. I will be also uploading supporting materials for this lecture, because I did not write down all the large matrices, which will consume even more time. So refer these materials. As you can see, this is nothing new, a very simple process. We have used the same steps to generate the stiffness matrix for a concentric triangular element. So it's nothing new. It's just simply that since the nodal degrees of freedoms tend to increase, then the rank of the matrix or the size of the matrices directly increases, which makes it hard for performing hand calculations, and you always need to resort to computer programs to do such calculations. So this is the part I intended to cover today. So we walked through a complete problem using a CST element or CST elements to model a bending problem, a plane stress problem for a beam element, which is subjected to traction load. And this is the same amount of calculations or the same type of calculations done within the computer, more sophisticated if you use more number of elements and more number of nodes, meaning higher order shape functions. So I think by now I was able to motivate you or provide you the necessary information to understand a computer simulation, and for you to motivate as to what is really happening within this finite element simulation. So I will stop the lecture now, since we have already come to the end of the lecture. Yeah.